Hi, we are Monique and Joey from Group 11, and we are working on torsional constant and twisting.
Torsion is the twisting of an object due to an applied torque, also known as torsional force.
Torsional constant, also known as polar moment of inertia, is a cross-section's resistance to torsion due to shape. The higher the torsional constant, the more resistant the shape is to torsion.
Our goal is to investigate the relationship between the 5 most commonly used cross-sectional shape profiles and the torsional constant when torque is applied to the end of each beam. We also experimented and attempted to design 2 creative profiles.
The finger load is kept constant at 120 Nm, and the following video will show you the experiment process and results of each beam.
By applying force on the lever of the beam will start to twist. You can observe the changes by looking at the longitudinal deformations, as well as by looking at the measurement of the angle twist from the cross-section. By applying the same force to all beams, you can compare the difference in twist between them. From our investigation and results obtained, we discovered that torsion is dependent on the polar moment of inertia, but not the moment of inertia. The I-beam is least resistant to torsion because the shear stress distribution is non-uniform. There are more in the web and less in the flange part. Thus, chances of failure to I section due to torsion is more, and meanwhile, the tube beam is the most rigid. This is because the shear stress distribution is uniform, thus making it safer than the I-beam. The results of our digital simulation indicate a different relationship between the respective profiles as compared to the physical ones. There are differences in the angle of twist, as the physical simulation utilizes cork as the material, while the digital simulation uses wood, as cork is not an available material on Caramba.
In real life, all buildings are to a certain extent resistant to torsion, depending on the profiles of the columns and beams utilized. The symmetrical placement of masses and profiles allow buildings to have the same torsional resistance on both sides. For our first creative profile, we designed it based upon the idea of a triangular truss beam, in which there are hollow centers on both the cross and longitudinal sides. However, our results show that this profile is not the most resistant to torsion, despite using the least materials.
To better showcase what torsion is, we have also created this profile, which illustrates how a beam twists and deforms when torque is applied. This beam is pre-twist. Hence, when we turn the lever down, the string of the beam further tightens, and it loosens when we turn the lever up.